Hi, hello, welcome again to Electronics Revision. Okay, with me, Mr. Jonathan Williams from Ysgol Sgwendraeth. These are the Carlam Cymru revision sessions, and I'll be doing electronics today. As I said, this is lesson 6. Okay, previous lessons you can get basically from the website. The session will last around 45 minutes, and if you've got any questions, please use a question and answer section. Triad yn ôl I chi. Okay, erbyn diwedd y wers, neu gwestiwn nesaf. Most importantly, the session it will be recorded and is being recorded, and the PowerPoint and any resources will be uploaded onto the e-sgol website. Have a look, type it in on Google, okay, type in e-sgol, and it'll come up, take you to the website, and then you can have access basically to all types of other revision sessions of the other subjects as well. Okay, and as I said, another 5 lessons of electronics. So moving on for today. First thing I would like to remind everybody about, there's a Carlam Cymru website, okay, where you can have access to recordings for the panel bit. Okay, the definitions and equations that you can't get access to from your data sheets. Please remember these. So I'll just remind you of what's the famous ones. You've got the VIR, you've got the VIR, be able to write that down at the start of an exam, okay, and be able to rearrange that. You've got your power equations, always handy. You've got the 3 of them. You've got your IV, your I squared R, and the V squared over R. I would say the other most important one is probably your potential divider equation, a gwahaniaeth potential bat, all right? Mae hwnna am ni fod yn ddefnyddiol iawn. It's sort of always useful for that one to work out voltages really quickly if you've got 2 resistors which are in series with each other, making a potential divider. Okay, you got the De Morgans, going back to the logic one. Okay, there's the break line. You change the sign. With the equation sheets today, okay, today we'll be looking at counters. So there is no real use of equations, but just make sure if you are revising, just have a quick look at those, okay, so you know where everything is in terms of equations, or just try and make notes next door to each one of those as to what they are, where they're used in revision. Today, heddi, ni'n mynd I fod yn disgwyl ar sequential logic systems. So basically using logic in order to switch things on, to latch things, and to count things, and to make sequences where they come on in certain order. So just a brief overview. Gan un pip fach I weld beth sydd gyda ni fan hyn I gyd. The classic SR latch. Right, with the SR, or should I say the not SR latch, because they are triggered with zeros. Okay, please remember, practice that, write it down. You might be able to draw that back from memory, triggered with zeros. You've got your clocked SR latch. Okay, so with the extra 2 NAND gates there, that would make things trigger with 1s. Okay, you can put a clock in as well. Okay, so it would trigger basically on the rising edge. You got your Dtype flip-flop, the classic Dtype, which will let you basically create a binary counter. We'll be looking at those. Major thing with a Dtype flip-flop is that it is rising edge. Whatever is on the D input will go to the Q output only on the rising edge of the clock itself. We'll have a look at that. You've got your transition gates. Transition gates are used basically to create pulses. They basically are used within Dtype flip-flops to create a rising edge, which basically transfers data. And there's an example there of the rising edge. It makes a nice little pulse. You will be required in order to turn decimal numbers into binary. Okay, again, that is something you need to practice. One thing I'll point out here quickly, you should be able from memory to go from 0 up to 10 and basically write the equivalent binary number down. In some questions, it's handy to write that down from memory before you answer it. Very, very handy. With the binary counters, okay, be able to basically chain together 2 Dtype flip-flops okay, together to make basically a counter. You've got your ripple counters. Your ripple counters, you basically chain together two of these together to make something which make a 7-segment display. Okay, light up as shown there. So looking at sequential logic. Right, moving on to the full A level. In component 2, you are required as well basically to look at sequencers. The sequencers again use the Dtype flip-flops, but with the extra logic gates, it makes it a little bit harder. Okay, using the logic in order to make things switch on, not in a binary scale, number scale, but basically in an order, sometimes that you decide, something that you've planned. So we're looking at those. Coming into the main sequencer, you are required to remember how to do logic gates. So know that basically your Boolean for AND gates, for NOR gates, XOR gates, and so on. So I'm going to look at some questions now and delve into like a couple of tips, things that you need to be able to remember when it comes to the exams themselves. Right, first thing we've got here, from looking at this, we've got a little bit of a problem where someone's coming up with some sort of game and you've got switches which says active low. Right, if you come across active low, that means they work with a 0. So 0 is going to make something to trigger. Okay, so for example, in this one, you've got little a control which goes along a wire. If you touch the wire, it goes to 0. That 0 then triggers something. Okay, so active low is when something's working. Looking at the diagram we got on the bottom here, right? The first thing that strings to mind, that is basically an SR, not SR latch. Okay, so is 0 coming into it will give me a 1. Okay, looking at the gates on the bottom here, we've got 2 1s. Two 1s will give you a 1. So this is the reset line. But when a 1 goes to 0, because it was active low, you win. 1 goes to a 0, you fail. Right, so that will change the logic. Once you get a 0 going into that gate, you get a 0, bang, there's a reset. So recognize that the bottom gate is the reset line, and the top one is your set. Okay. When you come to this type of thing, remember that if an input, you've latched something on, you've got a 1. If that changes, that stays on 1. That's the whole point of this, is that it works as a latch. So 0 will trigger it, but if that 0 goes to a 1, that will stay on 1 until you reset. Okay. Other questions they like asking with these type of things is, what happens if you have 2 0s going in? Whoa, if you have 2 0s going in, boom. Now it's not going to blow up, right? But you basically won't know what's going to come out of it. So you've got to have a 0 on one and a 1 on the other all the time in not S, not R latches in order to make them work. Okay? So byddwch yn ofalus yna, right? Mae rai fod gyda chi 0, 1 yn mynd mewn, chi ffili cael 2, 0, a pethau mynd I fynd yn lletwyth a ffarnol, os o'n I moyn pethau fel I digwydd. Okay. So having recognized we've got the SR latch, right? Maybe we want to answer some questions basically on it. So there we go. The subsystem we saw there, that is the not S. Okay, and it is the not R. And it is a latch. You could also call it the bistable. Right? Bistable, bi is one or the other one. Okay, so it's either the Q is on or the not Q. Okay, so have a look at those. Yes, latches, always handy. Right, looking at the sort of diagram we've got here, that switch S goes low. That means that's the trigger. Okay, so not S, 0 will trigger things. So looking at the switch F, we've got the 0 happening in this bit. So from the diagram, that was a reset. Okay, so looking at the diagram itself, we're going to start to draw it here. Now that 0 will trigger, give me an output. Okay, and it happens with the rising edge on the pulse going in. Stays high, we've got the reset coming in, so that reset there is basically going to cause my output to go back down to 0. Right, so P is the output, which is the Q1. Okay, so on the output itself, there was a pulse going in. Now, it's always handy to remember this. If you have an AND gate and you put a pulse in, you get a 0 until the other input goes to 1. If you got the another input goes to 1, then the output is able basically to flash. So this is always a handy little thing to remember. How to make something flash, you use an AND gate. Use an AND gate with a pulse going in, okay, and then you trigger the output to make a pulse by going from a 0 to a 1. Okay, so the output in this case, that's the that's the output which went high. You get the pulses coming through while it's high. So basically, you would end up with 5 counts basically on the display itself. Okay, so important summary from there. Recognize a not S, not R latch. Okay, click ed, dim S, dim R, click ed. There's the latch. Galvin bistable, dim problem go by. Okay, you trigger it by using zeros, and you reset it by using zeros. Okay, and the other thing, don't have 2 zeros going into not SR latches. Okay, because it gives you an indeterminate output. You don't know what you're going to get. Right, leads us on to basically the D-type flip-flop. As I said before in the introduction, with a D-type flip-flop, whatever's on the D input will go to the Q, but it only happens when you have a rising edge going in on the clock itself. This is the most simple that you can have diagram here. You've got a clock, you're looking at the rising edges. Things only happen on rising edges on D-types. So this is the data which is going in. It just happens the data is on rising edge, so I get that one. This data line there gets ignored because there's no rising edge on the clock. Rising edge on the clock, but it's already on high. We've got a rising edge and the data was 0, so bang, down we go. Not Q, it's going to be opposite of what the Q output. Okay, so there we go, right? So that's the crucial thing. That's just with one D-type flip-flop, right? Please remember that one. Big thing in the revision, look for the rising edge on the clock. Once you've got the rising edge, look to see what the data is. That data will get transferred to your Q only on those rising edges. So look to see what's there. Now, this is the classic where you can basically now chain together D-type flip-flops to make a binary counter. So you've got the clock coming in. It's got a high frequency of 480 kilohertz. You'll notice what you've got here. This is called a ripple counter because one D-type feeds into the clock of another one. So it's a ripple. Remember, this is the least significant bit. This is the most significant bit. Basically, most significant bit means it's got a bigger value than the least significant bit in terms of decimal number. Okay, so first thing I'm going to look here, got my clock, rising edges. So for the first one, rising edge will basically change what is going in. Okay, from the D goes in over to the Q. So every single rising edge will do something for the first. So in the first one, notice that this changes at half the frequency. If it was 480 coming in, the frequency of this one would be half of that, which is 240. Now then, got to be careful of this. Next flip-flop, now remember what's happening is, it's the not QA which is feeding into the next one. So, what I'm looking for here, strange is the falling edge of not Q, because the falling edge of not Q, of Q, will be the rising edge of not Q. They're opposite to each other. So this one, falling edge of the Q, falling edge on the Q, give you the rising edge on the not Q. If you're doing this right, you should end up basically with half the amount of the first one again. So this is what catches a lot of people out, is that the second D-type changes when Q goes low. Why? Because it is not Q which feeds the clock. Okay, so those arrows, I like putting those little arrows in, because it always tells me, yeah, something's going to happen on the falling edge. Because it is the falling edge makes the rising edge, which is going into the clock. So looking at there, the frequency, we've got a quarter of frequency on the second one, makes sense. And then there would be 1/8 of the frequency for the last one. Okay, so if I was looking at numbers, you got the 240 for the first one, 120 for the next one, and then you'd have 60. So for QA, you've got a frequency of 240. Okay, so the next one would be 120, as I said. Then you've got the 60. Then you've got the 30. So which one produces a frequency of 60 hertz? That'll be the QC one. Is the case with the binary counter. Okay, so practice basically drawing timing diagrams when it comes to binary counters, right? Can be tricky. Can be tricky. So key thing, for the first one, clock goes in, rising edge. For the second D-type flip-flop, it is the falling edge which triggers the next one. Falling edge of QA means you've got a rising edge on the not Q, which feeds in. Tricky, memorize it. So there's your binary counter. Right, so associated with binary, you have to be able to turn decimal numbers into binary and binary into decimal itself. Okay, so what we've got here, this is my method of doing it. Set up, find the right on the exam paper, set up the 2 to the powers, and underneath it, write down the value of each one. 2 is because we're talking binary, there are 2 numbers. That's where the 2 comes from. So 2 to the power of 0 is 1. So it goes up 2 times 2 times 2 times 2 times 2 times 2. Now where you stop, this is going to be your judgment. Now in this one, I'm going to go to 237. So I realize 2 to the power of 8 I won't need. Okay, so I need to make 237 now from all of these combinations. So I'm going to use 128. I'm going to use the 64. 128 and the 64, add them up. Okay, and that gives me 192. So I need to get to 237. Yes, I need the 32. That'll bring me to 224. Keep adding all the time. If I added a 16, okay, then that would take me above. Okay, that would have taken me up to 240. So I was too much. So I'm putting a 0 in. Yes, I need an 8. Should bring me to 232. I need a 4. Don't need the 2 because that would have taken me too much. I need the 1 again. So I'm adding the values of each one of these. Wherever I'm using it, I'm putting a 1 in. So that is my binary number. That's probably the quickest way, all right, in order to turn a binary number, decimal into binary. Now, binary coded decimal is slightly different. Binary coded decimal is made from 4 bits. So on an exam paper, I would write basically the combinations down. Now you need to go from 0, and then you go 1, 2, 3, 4, 5, all the way up basically to the number 9. So binary coded decimal is made up of 4 bits. That's the first thing. Always easy then to put the numbers down corresponding to that binary. What we do then, we break the numbers down. Okay, so if we want to turn that into 237, I'm going to look for new line. Start with 9 is the max number that I will reach. Okay, I don't need more than that when it comes to binary coded decimal. Binary coded decimal basically feeds into a 7-segment display. So I'm going to use the 2, I'm going to use the 3, and I'm going to use the 7. And I'm going to write down basically all of those 4 bits. So there's the 2, gone in. Okay, this is the 3 going in. And this is the 7 going in. Okay, so as you can see, a binary coded decimal number uses more bits. That's a disadvantage, right? So sometimes they will ask you, give an advantage of BCD and a disadvantage. BCD will need more bits than a binary number, as you can see there, right? So you compare that one to that one. But it is much quicker to convert a number into BCD. Once you've got all this written down, okay, I could give you any number now straight away. We're just using my little chart there to write down. Very handy. So you've got a binary coded decimal number. Right, we've got a binary counter here. That's the most significant bit, and we've got the least significant bit there. If you want to make a counter, so if you got counter going to a 7-segment display, the biggest number you can show on 7 segments is 9. So you need to reset on the number 10. So if you remember that a D and a B will go to 1s, I'm going to take 2 lines from the B and D, 2 1s, and I'm going to reset. Notice that is resetting with a 1. Okay, if there's a little circle next door to that, that's resetting with a 0. In this case, I'm going to reset with a 1, so I'm using an AND gate. 2 1s will give me a 1. Boom, resets. Mae'n ailosod gyda 1. So did mwyaf arwydd y cawl, more significant. Did lleiaf arwydd y cawl, you are. Okay, so whenever you have a binary counter, and if you want to basically reset it, and turn it into BCD, you have to reset on the number 10 itself. So it's always handy, basically. That little chart is your top tip when it comes to BCD. If you're going to convert from from decimal into binary coded decimal, okay, that's your chart. If you're going to go into binary, do that little chart there with a 2 to the powers. Okay, practice that. Write it down quickly so you can do it bang. 10 seconds. Okay, it'll save you so much time basically in an exam. Associated again with Dtype flip-flops are things called transition gates. Now, transition gates are used in the world of electronics to basically create pulses, okay? And a rising edge pulse, which is used to transfer data. So in this particular question, if I have a 0 going in right at the start here, that means a 0 right at the start over there. But if I look at the logic, that would be a 1, you've got a 0, and you've got a 1. So 0 and a 1 goes into an AND gate, where you got coming out. It would be basically 0 to start with. Okay, so at B, I have a signal 1. Okay, so I've got a 1, I'm showing that 1 there. Then, what happens if this 1 goes, north goes to a 1? Well, I've got a 1 there straight away. Logic will change in each one of these. But crucially, there is a propagation delay. It takes 10 nanoseconds for logic to change in gates on average. Now that delay is used in transition gates for our advantage. Okay, so there's the input, it's changed high. So the signal at B, when this changes, is going to take an extra 30 nanoseconds before it changes. Okay, so if you've got 0 goes to 1, 0, 1, but that's going to take 30 seconds, nanoseconds after that change before the signal B will change. Now, if you're looking at what's going on the output there, that output gate basically will see a 1 and a 1 for a certain amount of time. Now, it won't happen straight away. That 1 and a 1 will give you a 1 because of an AND gate, but there's a 10 nanosecond delay before it does it. You're looking at these two to see what the inputs are going into the transition gate. So at this particular point, we've got a 0 and a 1. Now that 1 and a 0 is going to give you a 0, but not give it straight away. There is a 10 nanosecond delay before it goes down. So what you're seeing there is basically a pulse. So that pulse there, total, is 30 nanoseconds. Usually what happens is you look to see how many of these gates you've got, and those gates there will give you basically the length of the pulse that you've got down there. So if you wanted to make a pulse, just so we say, only 10 nanoseconds in size, I would only use 1. If you want to make 20 nanoseconds delay pulse, I would use 2 of these NOT gates. 3 of them will give you 60. Okay. So, yeah, number 1, revision on that. Transition gates, know their use. So it's to create basically a pulse of a certain duration. Used in Dtype flip-flops to give you a rising edge. Propagation delay means the time taken between the input and the output being able to change. So always think yourself, right, what my logic is like at the start. So from there, recognize what is the logic going out of the gates. When something changes, okay, these timing diagrams again become very, very handy. Okay, so there's your transition gates. They do come up. Right, moving on to sequence generators. This has been component 2. This is in year 13. Right, when it comes to the exams themselves, component 2, not in the AS. Right, first thing you've got to recognize about sequence generators is you always have something that we call a main sequence. So a main sequence is made up of states all going around. If you don't have a state and it doesn't go into this main sequence, we call it a stuck state. Now, if you've got a stuck state, that is bad, because when you boot up a system, it does not give you access to main sequence. So on power up, it will stall, right? It will basically freeze and can cause crashes, okay, in computer systems. So in the main sequence, what we've got there are unused states. Unused states, you always try and make them feed into the sequence, the main sequence itself. So identifying the stuck states. Don't give me 111, okay? It would be called states number 6. Okay, so they're looking for that S6 in there. It is stuck. Any unused state, which is unused state, so they're not in the main sequence. Okay, they have a choice there of 3 things. Okay, got the S4, 5, 3, and 7. So it's on power up. If the system should start on S4, when you've turned it on in the first place, for a sequencer, first pulse will take you to the S5, second pulse will take you to S3, third pulse into S0, and then the fourth one will take you into S1. So you've got 4 pulses. Okay, now the design of how to make that, we usually use truth tables, okay, to make basically a sequence. Now, the important thing to recognize when you've got a main sequence is you always look at the sequence you're on now, and then you look to see what's coming next. Okay, so what's yn disgwyl I weld beth sydd gyda chi nawr, beth sy'n mynd I ddod nesaf yn hollol bwysig. The sequence generator, you are required to be able to show how to wire it up. Okay, normally speaking, with sequence generators, you will always have logic in order to get that special sequence that you want. So looking at DA linked into C, no problems there. You're looking at DA into C. Now, this is where you have to recognize gates. So we got there, that is a NOR gate. Okay, in NEA. But recognizing that, you should then be able to draw the logic gate for it. Okay, gwneud yr adwy gyfer y NEA I hunan. It's a pretty poor drawn. Going into that NOR gate is A and C. Just recognize that line there and the O sign. Okay, and feeding into it, we've got the A and we've got the C. Just one gate is needed to show that. Just draw that a little bit better for you. So there's the NOR gate. Right, recognizing this one, you've got the B and C line on top, automatically, bam. Okay, that is the NAND gate. And NIAC, okay, those gates are always useful. Remember that you can use those to draw instead of AND gates, OR gates, NOR gates. So looking at that, we've got B and C going into it. There's the B. And I'm going to take a C going into the AND gate, NAND gate. And that goes into the DC. But finally, okay, completing that circuit, what you've got to remember is that the clock input is common. Got common clocks. Now that is the biggest difference between a sequence generator, sequencer, and a binary counter. So common clocks, they can work basically on very high frequencies. Okay, so high frequency going into a sequence generator will not cause basically problems, right, on the outputs. Now what you can have when it comes to binary, you can have misreadings. So high frequency does not cause a misreading on sequence generators. Binary counters, high frequencies can cause misreadings. So what happens? The input changes before the output does. Okay, because of this propagation delay between the input and the output. So that is a problem at high frequencies. Remember that, that's a top piece of revision for you. Okay, so when it comes to sequencers, be ready to draw a sequencer, common clocks. Be ready to look at your logic and recognize a gate which feeds in basically on the sequencers. Right, now this is where I was talking about the main sequence, being able to draw basically what comes next. Right, so if someone gives you a synchronous counter and asks you to design it, or a synchronous counter, now in this particular one, truth table has been given already for you. You have to fill it in. But the key thing is this: whatever is on the second line is on the next output. Or if you want to think of it on the other way, the next output feeds onto the second line. So the 0, 1, 0 will feed into 1, 0, 0. So that automatically goes to the next one. Will feed into 1, 0. Okay, so notice basically whatever you've got on the next output goes to the next line. Now in this particular sequence, that last line goes back to the start. So this main sequence is using basically every possible thing that you can have. Sometimes you might only have like 4 lines which are in the main sequence. Okay. So this one uses the whole sequence array. Now, what you have to be able to do sometimes with these is come up with a Boolean expression. Now, this one is asked for, what are the Boolean expressions for just the DA? So with a DA, you're looking to see where the ones happen. And there are 2 options here, what you can do. You can use a Boolean simplification, or you can use a Kano map. Now, I've posted that Kano map next door to there. That was not given in an exam. So sometimes it's handy just to memorize how to draw a little Kano map like that. Practice that. So each one of these ones now, I'm looking to see what the Boolean is for each one of them. Okay, in terms of A, B, and C, just where the ones are. Now, what you could do is to try and simplify that by using Boolean, but that's something that's really hard when you've got loads of terms. Now, if you can transfer that into a Kano map, it becomes really easy to simplify it. So I'm going to just transfer the ones in. So looking at whether C is 1, whether B is not B is the 0, where the A is 1 there. So I'm looking to see where I've got a 0 on a C, a 1 and a 1. And then I go for the groupings. Now here I can only group in 2s. Can't group in 4s there at all. So 3 groups in total. So I'm now going to try and simplify, take that group there. What's common is the C, and I've got an A. Next one is common there is I've got an A and a B common on that line. And then the final 2 there, I've got common there is there is a C and there is a B. Okay, so it's easy to do that. If you were trying to do a Boolean, okay, what you're going to try and do is look for common terms. So there, I've got CB common in these 2. Would leave the not A and an A, and that would basically turn to 1. So that simplifies to the CB, which is there. All right, I'm going to try and look at these 2 here. So what's common there is basically the C and the A are common in those 2. Take the B's out, and that will cancel. B or not B gives you a 1. And then final 2, I'm looking at grouping those 2 again. What's common there is the AB. Take the C out, the C or not C cancels. So if I look at it, everything in the bracket will cancel to a 1. So I'm left with the same terms. Little bit more difficult in an exam situation. Right? So if you want to try and remember basically a Kano map, often in a Kano map might be given in the paper. Right? So you're flicking back in the paper if you can't remember how to do a Kano map. Look to see if there's one there. And then from there you can basically copy the 1s and the 0s for the A and the B. Right? Lot easier. So main thing with main sequences, truth tables, when you're creating a truth table which goes with a sequencer, remember, whatever comes next basically goes onto the line below. Now, sometimes you might have to come up with this on your own by using basically logic gates. They might give you a logic gate, and then you have to look what's going into it, and from there working out what happens on the outputs. Okay, that's the other option that you have there. Okay, so that covers basically all the variations in terms of counting. Okay, using binary counters, you've got your transition gates, and you've got your sequences. So just to have a quick recap on what is required from memory, I would say, so from memory, being able to draw a not S, not R bistable latch is really important. Triggers with zeros. Being able to draw a transition gate. Each one of those gates gives you the length of the pulse. Remember that one. With a binary counter, you would have to maybe draw the binary counter, practice that. Okay, what's the problem with that? High frequencies might give you misreadings because of a propagation delay. With the binary counters, the rising edge will trigger whatever goes from D over to Q. If you start chaining them together, remember the not Q is what feeds into the next one. Okay, so it's the falling edge of one which triggers the next one. Okay, didn't look at a clocked SR latch tonight. Basically 2 gates. Okay, and that would be then triggering with ones. Okay, know how to turn a decimal number into a binary number. Okay, but on a binary number back into a decimal number. Didn't look at hexadecimal tonight. Okay, ripple counters. So with a ripple counter, you can put a ripple counter into a decoder. A decoder then goes to a 7-segment display. If you want to chain them together, the output of D basically goes into the next one. If you're looking at Dtype flip-flops and you look at counters like in this one here, you've got to remember, if you've got a zero next door there to the reset, that means that you are resetting with a 0. Okay. And then you've got your main sequence. Stuck states, they don't let you have access to a main sequence. So avoid stuck states at all priorities. Unused states have to feed into a main sequence. Remember that. Know your gates in order to feed in and design main a sequencer. A sequencer has got common clocks. Common clocks mean that your high frequency will not cause problems because there's no propagation delay between each one of them. So there's your summary. Any questions? Type them in. I'll try and get back to you. Jeff and Val, thank you. Hope to see you again.